Good morning. This is better. Welcome to the morning session. And I told the organizers that I have to leave at noon, and they asked me to be the morning chair, meaning that everything will be well in time. So I will be a tough chair. I would be anyway, because that's my nature, but I really have this flight restriction. So for the speakers, I saw like this: when you have 5 minutes of your speaking time left, and then I stand up when you are on your discussion time. It's up to you how much of your discussion time you use. Okay, so now we have the pleasure to hear Katja Nowack from Cornell University talking about magnetic probes. Please.
Yeah. Okay, thank you very much for the introduction, and thanks to the organizers for giving me the opportunity to be part of this really exciting workshop. I've really enjoyed all the talks so far and really learned a lot. Yeah, I'm staring at that too. It's distracting. I don't know if there's a way. Oh. Where is the mouse? Oh, there. Okay. Hide video. Maybe there's a hide video. Hide float. There we go. And then maybe also hide the. And also the other. Oh, but now I don't know. Well. Better? Yeah. Okay. All right. So when I actually got the invitation, I wasn't quite sure how it would fit in the theme of the workshop. So I gave a maximally vague title. What I'll really be focusing on today is recent work we've done to try and understand how the current actually flows in at least one type of quantum anomalous Hall insulator. Okay, but before I go there, let me give you like a pretty broad perspective of why technical. What am I doing wrong? Do I have to point at a specific or is it maybe I have to kind of click on the back on the slide and then yeah, now it works. I think I was in the Zoom with the yeah. Okay, cool. So a pretty broad perspective, why are magnetic probes actually an interesting tool to look at quantum materials? And here I really think of those kind of magnetic probes that just measure the stray magnetic field coming out of a sample or a material. And that could be scanning squids. That's a technique I will talk about, but it might also be scanning NV centers and diamond microscopy, as John Way described yesterday. All right, and so the argument is very simple. Magnetic moments and moving charges are really at the heart of many of the kind of phenomena that we're interested in materials, and both produce stray magnetic fields. And so just that simple argument tells you that local magnetic measurements or a local magnetic probe can provide potentially a unique window into the physics of quantum materials. And just to give you some examples of what a magnetic probe can do, I'll very self-servingly give you a few recent examples from my lab. So if you think about a magnetic probe, you probably think like, well, I can measure magnetic properties and maybe also the magnetic response. And so, for example, you can look at just using DC magnetometry, you can look at vortices hanging out in superconducting, in this case, niobium titanium nitride strips. This is interesting to our collaborators at IMEC who work on superconducting digital circuits made from niobium titanium nitride. Or you can measure the magnetic response, say, of a magnetically frustrated material. This is a measurement on thin film terbium indate, which is a spin liquid candidate. And this is just one measurement in one location, but of course you can do that also spatially resolved. All right. Nice aspect of magnetic probes is they're really not surface sensitive. And so you can probe functional devices and process devices. If something covers, the active region of your device, it doesn't matter as long as the stray magnetic fields actually get through, right? So we, for example, image these focus ion beam defined microstructures, even though they're heavily processed with a gallium focused ion beam, Or you can even look at kind of like a top-gated Hall bar structure. Here we actually look at the magnetic structure in that Hall bar. And there's even kind of an oxide and then a top gate on top of this device. You can use magnetic probes to visualize electronic transport. And so I'll talk a lot more about that in this talk. You can also use it to visualize magnetic textures. And so we'll get back to this picture here in the talk. This is actually my only image using scanning NV center and diamond microscopy. There must be a shorter way to say it. Which I actually also do together with Greg Fuchs at Cornell at room temperature. And then finally, one setting point of a local magnetic probe is you don't only have to think about using it for imaging. You can also think about it as using it as a very sensitive magnetic property measurement system that's local, by that extremely sensitive. So you can use it just to probe samples with extremely small sample volume. And so, for example, we've successfully measured the superfluid stiffness in ionic gated molybdenum disulfide, even though that superconductor is atomically thin and the sample is only about 10 micrometers across. And so a local probe actually gives you enough sensitivity to do that measurement. All right, now zooming in a little bit, why do you might want to kind of investigate electronic transport on the local scale? So also here, a pretty simple argument. Take your favorite material, pattern into a Hall bar, and then you do a transport measurement. Well, you can think of your material maybe as, you know, being made up out of like a teeny tiny microscopic resistor network. And sure enough, if you know what bias current or bias voltage you apply, you can calculate, given this resistor network, what current is going to flow, what voltage values are you going to measure, and then you can even also predict all the local currents and voltages kind of in this sample. However, if you do the inverse, and that's what you do when you do a transport measurement, well, you might know what bias voltage you applied, you might know which current was flowing, and you get these two values here, but it is absolutely impossible to then say how do the local currents and the local voltages actually look. The only way you can do it is making pretty strong assumptions about how this underlying resistor network actually looks like. And sure, there's like a lot of examples where, you know, for instance, assuming that this resistor network is uniform is a good assumption, but there's also kind of an increasing amount of examples, and these are really only a few examples of where that assumption maybe breaks down. So two examples are actually imaging of the current density using nitrogen vacancy centers of hydrodynamic transport. It's nitrogen vacancy centers here, and this is the scanning squid on a tip. And so here, even like a description with a resistor network isn't quite appropriate. But the other examples are really examples where there's unexpected non-uniformity in the sample. So for instance, the scanning squid on the tip has revealed trivial edge conduction in some graphene devices, which can give rise to pretty pronounced non-local transport signals. We have measured these serum iridium indium 5 focus ion beam defined microstructures, and we explain pretty unusual transport behavior in these devices, but just finding that the superconducting transition in these devices is extremely non-uniform due to a kind of built-in strain in these microstructures. And then there's other examples where, for instance, here in LAO STO, there's an interplay with structural domains in the STO modulating the local conductivity in the material. And then here's actually a pretty exotic magnetic imaging technique, scanning quantum cryogenic atom microscope images of a nematic transition in a nictide. And they found a strong modulation of the local current density. So these are just some examples. Now let's jump in and talk about quantum anomalous Hall. I don't need to introduce the quantum anomalous Hall effect to this audience. So it was first realized in thin film magnetically doped topological insulators. And the idea there is when the magnetic dopants magnetically order, you open an exchange gap where all the magic happens. And then the key signature of the quantum anomalous Hall effect is a quantized rho yx and a rho xx that drops pretty much to 0. And this is realized in this sample there's electrostatic gating, and at minus 1.5 volts, sure enough, you're in the quantum anomalous Hall regime. And of course, the quantum anomalous Hall effect at this point has been realized in many other material systems, and I even can keep track. So the dots here indicate like the ones that I may have overlooked, but the family of materials where the quantum anomalous Hall effect is found is increasing. Okay, so now we can ask, how do we actually expect the transport current to flow in a quantum anomalous Hall insulator? And at least the literature has a pretty strong consensus. So there are these dissipationless edge states that leads to nearly vanishing rho XX. There is confinement along the sample side wall should ensure conduction is one-dimensional. There's chiral edge conduction. There is a 1D edge current, and so forth. So the conclusion, the consensus is very clear. The transport current is going to flow along the edges in these samples. Okay, great. And we have just the right tool to image exactly that. So here's your favorite magnetic sensor. If you have a current flowing in a sample, the Biot-Savart law tells you how the magnetic field looks like that current produces. Then you come in with your favorite sensor. In this case, I wrote it down for a sensor that detects the Z component of this magnetic field. And then there might be a point spread function associated with your sensor. And then this is the signal that you measure. And it turns out if the current is two-dimensional, you can actually, from an image of this detected signal, you can reconstruct what the current density was. And in our case, this sensor here, or this magnetometry loop, is connected to a superconducting quantum interference device. And that's why we can measure the magnetic flux threading that loop. So normally a squid is just a superconducting loop with two Josephson junctions. Our squids are actually pretty complicated in the end. The junctions sit somewhere over here, but the squid is kind of stretched out over like millimeter length scales. The sensing is really done by the sensitive area at the far end here. So here you get a picture of the squid pickup loop or squid loop. In this case, it has an inner diameter of about 1.5 micrometer. There's also this field coil, which I actually will not describe in this talk, but the field coil is really important to enable local magnetic response measurements using the squid. Okay, and then we take this really big chip, align it under a fairly shallow angle towards the sample, scan it around, and that's how we take an image. All right, and we do this in a 4-Kelvin system, but also in a dry diffusion refrigerator. And here are some pictures of that. But the main point is that the fridge has a base temperature of about 10 millikelvin, and we have vibrations in the system, but they're reasonable enough for us to be able to do the kind of imaging that we do. Okay, so now that brings me to the sample that we actually image. So we look at a chromium doped topological insulator or chromium doped bismuth antimony telluride. These films are grown at Penn State in the group of Nitin Samas and by Run Zhao. And they also made or patterned these films for us into Hall bar structures. And the Hall bar is about 75 micrometer in width. And the measurements that I will show in my lab were done by Matt Ferguson. He actually graduated a little while ago and is now a postdoc with Andy McKinsey at the Max Planck Institute in Dresden. And you might see him at some point. He might be on the job market at some point soonish. But all right, so here's some transport on the sample. So below 100 millikelvin, we get a quite nice quantization of RxY, while at the same time RxX drops to very low values. This is at a specific gate voltage. We can gate the sample using a backgate and then discover where backgate voltage space we actually have the quantum anomalous Hall regime, and that would be this plateau and the corresponding plateau in RxX down here. Okay, now we are set up to image. So let's see. So I show you where roughly the field of view is in the Hall bar that we imaged. So first of all, you get an image of the DC magnetic flux. And that image just tells you, okay, yes, the sample is magnetic. So there's lots of stray magnetic field just coming from the magnetization of the sample. Then you apply a current at a frequency of about 100 hertz, a low current. You apply it at a finite frequency so that you can with a lock-in measurement, just detect also the flux that's created by the current. And so that is this image here. So that's the squid flux, or the flux that the squid detects from the magnetic field produced by the current. This is how it looks. And already just from this flux profile, I can tell the current isn't flowing along the edges in this sample. And we can try to do it one step better. Because of the noise in the image, it's a little tricky, but you can do a current reconstruction and really find that the current is also flowing in the bulk in this sample. We can do a bit more careful studies. So now I'm constraining myself to just taking a line cut through the sample and then tune the backgate voltage through the plateau. And I'm showing directly the reconstructed current density in the sample. And so at this black trace, so that corresponds to the colors of the dots here, we get a quasi-uniform current in the bulk. As we tune backgate voltage, things start changing a little bit. That current density seems to split into two halves and then getting squished towards the edges as we tune through the plateau. But sure, the current density profile changes as we tune through the gap. But it's certainly true that in most of these traces, the current really flows in the bulk. Oh, I have to speed up. I'll cut a little bit in my discussion time. But if that didn't convince you, let's just look at directly at the flux profiles. And just let's consider some example profiles. Let's consider a uniform current through the bulk, current flowing along the two edges of the sample, and maybe a current that just flows along one of the edges of the sample. And let's assume the total current in all these pictures is the same. So you have like these model current distributions here. And then we know our point spread function very accurately from imaging known sources of magnetic field. So we can model how the magnetic flux will actually look like based on these current profiles. And this is how the flux profiles come out. And if we compare to the data, say again, like a line cut here through the middle of the channel, then it really fits a current density that flows through the bulk of the sample. And I can even also go and compare that to the experimentally measured kind of current profile that I get when I just take a profile through the gold contact, where I really know the current should be flowing through the interior of the channel. Okay, so we definitely observe a regime in which the non-equilibrium transport current, so that like we apply a transport current, predominantly flows to the bulk in the dissipationless regime. We take care that the current is low enough that we really, in the simultaneously measured transport, have good quantization in RxY and Rxx. I just want to stress that doesn't imply that there are no edge modes and that persistent currents are absent. It just means that if there are edge modes, they at most carry a small fraction of the transport current that I apply. Okay, and we've also looked at a second sample fabricated from a similar thin film, and we saw in that sample also the current flowing through the interior of the sample. And interestingly, in that sample, it was just like nothing changed as a function of gate voltage, only the transport coefficients. It just stayed uniformly in the bulk throughout the whole quantum anomalous Hall plateau. All right. Let me see. So I was quite shocked at this. I really expected and wanted the current to flow along the edges. And just to, then we went back and looked in the ancient, not quite ancient, but like in the quantum Hall literature, and discovered that, you know, it's actually not so clear even in quantum Hall if the current truly is confined always to the edges of the sample. And so I'm not saying this bulk picture is what's truly going on in the samples, but I just want to remind everybody about an alternative picture, how to think about transport also in the quantum Hall regime that doesn't involve any edge channels. So let's say you have you know, your favorite material being in the quantum Hall or quantum anomalous Hall state. How you can describe it is with a conductivity tensor where sigma xx is very, very suppressed and sigma xy is quantized. And you can actually go and calculate the local potential landscape that would be associated with such a conductor. And that is how it looks like. So this is the electrostatic potential. color-coded. And you see that along the sides of your Hall bar, you lie along an equipotential line. So you measure Vxx equals 0. And then you do get the appropriate voltage drop between the two sides of the sample that gives you an RxY that's equal to each over E squared. And if you look at this further and ask, like, okay, if this is the local potential, how's the local current going to look like? Well, you can say, well, current should be conductivity tensor times the electric field. Because of the off-diagonal nature of the conductivity tensor, it really means here that the current follows equipotential lines. So if you look in the middle of the channel, you would expect that the current flows pretty uniform through the channel in this picture. And it's worthwhile to point out that you can do these kind of simulations also with non-local geometries or Corbino-Dest geometries, and this bulk picture always gives you the right answer as to what you would even expect, say, in non-local transport experiments. All right, and then one nice feature is here, this kind of picture predicts that there are so-called hotspots. The current doesn't come uniformly out of the contact, it actually comes out concentrated at these corners of the contacts. And that's something that we can actually also see. So here's the DC magnetization that tells us where actually the line between the gold contact and the material is. And these are the flux images associated with the transport current. And we really see a pile of flux right here, which actually means the current density is very concentrated right here in this hotspot. So we actually even observe this hotspot at the source contact. And if we flip magnetization, this is taken at a slightly higher current than this, so it gets a bit more fuzzy. But we see the hotspot changes location when we flip the magnetization, which essentially flips the sign of the off-diagonal sigma xy. All right, and something like this has, of course, been seen in an interquantum Hall with a very cute experiment that involves kind of bubbles being created in a superfluid film covering the sample, and the bubbles form because of like increased local dissipation. We can also image this hotspot as we tune out of the quantum anomalous Hall regime, at which point kind of the Hall angle, which I defined for you here, gets smaller and smaller, and the hotspot kind of softens as you decrease the Hall angle, and so that's kind of neat. I was going to look at the quantum Hall effect. It's really interesting to look at this paper where Klaus von Glissing's group essentially reports local potential measurements while applying a transport current in quantum Hall samples, and concludes that there must be also a current flowing in the bulk in the quantum Hall regime. And there's a lot of other things that are interesting. I will skip maybe as a way to advertise. We have one other measurement mode that is interesting to look at. We can modulate the top gate that's on the sample slightly, and actually the magnetization response to that top gate modulation. And that is interesting in itself, but also we found that when we tune deep into on the one side of the exchange gap, we get one response, a stronger response, but once we tune through the quantum anomalous Hall regime, we get a much weaker response, and we kind of interpret this signal as a local marker of where the Fermi level is locally in the sample, and the kind of substructure we see in that measurement mode really nicely matches with the observed current density that we see. There's another whole story that I could tell about current-induced heating in these devices, which is interesting. If we analyze it quite carefully, and we think we can actually, in a way, where's the image? We can also image local dissipation in these devices, at least at sufficiently high currents. That's for another day. I will thank everyone. I want to kind of put up my acknowledgements, especially this is relevant for this talk. So I thank Rune and Nitin for providing us with the samples, and then Matt Ferguson again for doing these beautiful measurements. And then I'll put up my summary and finish here.
Thank you very much. Questions? Yes.
Well, thanks for the beautiful talk. Did you measure the temperature dependence of the current per phi?
Let's see. So we did a lot of temperature-dependent transport. We also did, it's probably in here, we also did a lot of temperature-dependent imaging of line cuts. Yeah, this data is mainly taken on that second device that kind of had everything uniform throughout. So we only ever got to see a uniform current distribution, no matter what we were doing. On the first device, I don't have quite as much data as a function of temperature. Pretty sure we have some 4 Kelvin data, but I have to look back. Yeah, yeah. But it is so it's interesting, and maybe to some this might be unsatisfying. But I'm actually so that there's a strong, like in transport, the 2 devices that we looked at look actually very similar. They both show quantized transport, yet the local current distribution in both devices looks very different. And so that is kind of maybe concerning on the one hand, but also exciting on the other hand, because it really shows that, you know, different local current distributions can give rise to quantization. Yeah, so it's a positive flip on this.
Okay, there's another question.
With this flux to current conversion, can you still distinguish between, or with what resolution can you distinguish multiple channels in some disordered landscape from a really uniform current flow?
So I have slides prepared on the spatial resolution. I won't pull them up in the interest of time, but I'm happy to show them. So we kind of, in this experiment, put our spatial resolution, depends on what criteria you choose for that, at about 2 micrometer. And so if there is some percolative part that like folds back onto itself very many times within 2 micrometers, then we wouldn't be able to spatially resolve that. But still, you know, there's strong constraints on how such a percolative path has to look like, because it, you know, in the end, it has to give, like, if you zoom out, the kind of average current density, it has to match what we see. And then it also has to give you quantization. So I really want to stress, like, the experiment. The reason why I show line cuts is that we had to do this experiment at extremely low currents, and the currents have to be low so that we assure that really we have full quantization of RxY and RxX. Yeah, and yeah, and it's hard. Like, if once you come up with a percolating path, then you know, it comes close to itself many times. So in a lot of pictures, you actually would lose quantization if the current would go through the sample in that fashion. So that's kind of like the, yeah.
Okay, one more question, and the next speaker can already go and put on the slide.
Thank you for the beautiful talk. Here. Naively, let's say I try to understand, like, your screen directly probe the flux, magnetic flux.
That's right.
Then you interpreted the flux comes from the current flow directly.
That's right. And so there's some trickiness with that, and that, for instance, like, but so when we do the reconstruction, we can, for instance, look like how much current is actually flowing in the sample. And we confirm that the amount of current that we reconstruct is also the amount of current that we send into the sample. That's a good sanity check.
Now, your question related is like, we know in quantum anomalous Hall, there's an orbital magnetization. Then, like, what you directly prove from the bulk is maybe orbital moment, or actually is really exclusively current.
So, I mean, because we do a lock-in detection, we really kind of exclusively look at the flux that's, you know, modulating appropriately with the, so we like the orbital magnetism that's not modulated by me applying a varying transport current. That should be part of, like, what I see in the DC channel. But there's, in these systems, there's also real magnetic moments and real magnetization coming from ordered magnetic moments. So you can't really easily disentangle what is like orbital magnetization, what is just like ferromagnetism, right? Or, yeah.